Yes, so today we have Professor Adam O'Neill from UMass Amherst coming to talk about the tight security of threshold Schnorr signature. So please take it away.
Thanks. Thanks for coming. Since it's a small group, I'd really like it to be interactive. And if you have any questions during the talk, just feel free to ask and we can discuss. So I'll talk about kind of some ongoing work about security of Schnorr signatures and then extensions of Schnorr signatures to threshold Schnorr signatures. It's joint work with my student Gavin and also Georg and Marek at TU Vienna. So some background on Schnorr signatures, which isn't really important for understanding our results, but if you want to understand how Schnorr came about, there was first what's called Schnorr's identification protocol, which is basically a proof of knowledge of discrete-log. And it can be made non-interactive using Fiat-Shamir, right? And you can like incorporate, it's using a hash function, and you can incorporate a message into the hash function to kind of make it a signature scheme as well. Okay, so it's quite old. I mean, this is from the late 80s, early 90s. And today, you know, it's one of the most widely deployed pieces of cryptography, often in the form of EDSA. So that means that basically what that means is Schnorr implemented over some particular curve, listed Edwards curve. And Schnorr is, as I said, it's used all over the place. Here's just a few examples. So Schnorr is now used by Bitcoin, for example, since I think 2021. And it's also used in a variety of other places. There's actually, I guess I didn't put the link to the site, but like there's a website where it lists like 200 or 300 uses of Schnorr, and you can see a lot more there. Another thing that's nice about Schnorr is the algebraic properties. So one reason why Bitcoin and other practitioners and in other applications, they like Schnorr is because the algebraic properties give rise really naturally to some nice types of advanced functionalities. Like you might have heard of threshold, blind, or adapter signatures, and those can all be built based on Schnorr.
What are adapter signatures?
It's something for, yeah, it's a good question. It's something for cryptocurrency. Yeah, I'm not actually aware. Yeah, but, yeah, it's just I say, yeah, I haven't worked on that. Okay, so just so everyone's on the same page, I'll just define the basic Schnorr signature scheme. I guess probably you already know, but it wouldn't hurt to review it. So in the setting of Schnorr, we have a cyclic group of prime order P, and it's generated by little p. And we have a hash function, which you can think of taking like a pair of inputs or just concatenation of a group element and a message, and it spits out something in ZP. Okay, and to define the three algorithms of Schnorr signatures, I write them here. So you sample from ZP in the key generation algorithm, you sample from ZP and get a little x, and then G to the X is the public key. The signing is randomized. So when you sign, you pick a little r, you exponentiate to get big R, right? And you compute little r plus Cx, where C is the hash of R and M. And you output R and S, and then, I mean, there's a simple verification equation that can verify. Yeah. Everyone good with this?
Like, is that
Hashing the M? Yeah, because otherwise, I mean, that's the only place that the signature is depending on M, right?
I mean, you need to hash M. Is it to like reduce malleability? Both of you want to reduce the size of M, because if M, you want to hash M to the curve.
Yeah.
Is it important for other reasons? Like, it's important to reduce the size. Because if you had like huge thing.
What do you mean, like hashing M as opposed to doing what? Like, M is already in the group, but what about R?
Oh, okay.
Yeah, like you need,
Sure.
I think it's, yeah, you need R and M input for that. So Schnorr, obviously, since it's been around for, I guess, 35 years or something, has been a subject of intense study, but there's two kind of issues or drawbacks in the analyses that have persisted throughout the years. One is that basically all positive results that I'm aware of for Schnorr rely on the random oracle model, right? And we get to what the random oracle model is, but that's one drawback. And then even if we are saying, okay, we're okay with the random oracle model, the main problem is that there's a large gap between the known upper and lower bounds on the security of Schnorr in the random oracle model, right? And this will be, so we don't do anything to eliminate random oracles in this work. We just focus on the gap between the upper and lower bounds of security. Okay, so in other words, we're just asking a question: how hard is it to break Schnorr in the random oracle model?
Yeah. Your presentation is cut off at this point.
Oh, really? On my screen, it's fine. Okay.
Can you maybe share again?
Sure. Yeah. So stop sharing and then.
That is. Oh, much better.
Is it better?
Yeah.
No, it's like,
Oh.
I don't know. It's kind of
But
difficult.
it's
Okay. So yeah, so just to recap, like we're asking the question, how hard is it to break Schnorr in the work? And just to give you like a sneak peek of our results, so I'll go through a bunch of definitions and stuff. But if you want to just know basically what we do in the work, we give a type reduction for from security of Schnorr signatures to the something called circular discrete logarithm problem, which is a new variant of discrete logarithm problem that's that is also just is also non-interactive and falsifiable, just like regular discrete log problem. We show that the circular discrete logarithm problem is as hard as discrete log in certain idealized models, so like some variant of the generic group model and so forth. And then we also show that CDL is applicable beyond just basic Schnorr signatures, and we look at threshold Schnorr signatures, in particular Sparkle Plus, which is a recently proposed threshold Schnorr scheme, and we show that under static corruptions, you get a type reduction from security of Sparkle Plus to the CDL.
And these reductions, are they in the random oracle model?
Yeah.
Okay.
Yeah, they're all in the random oracle model. Okay, so I guess I've given this talk various places, so the background has been different, but just so in case you don't know, I'll define the discrete logarithm problem. So yeah, I like to use these games with initialize and finalize. So what happens is initialize executes, right? And it chooses a challenge, g to the x. The adversary is given this we call it h, and it needs to compute x. And there's a unique x, right? So it needs to compute that x. And as usual, you find the advantage is the probability that the adversary wins the game. And then here I've just written the definition of unforgeability just for a signature scheme, just written it in terms of Schnorr itself. So, I mean, I guess, again, like I'm sure you know this, basically you just ask, the adversary asks for signatures on messages of its choice, and then it needs to produce like you see finalize takes this R star and S star, which are and M, which is supposed to be the forgery. And if like an S was not received back, or sorry, if R star and S star was not received back as the answer to query M before, then and the signature verifies, then it's forgery. So again, we have the advantage to find this, the probability that the adversary wins. And so also, of course, it's important to talk about the random oracle model. This is a very interesting topic. It's an idealized model for cryptographic hashing, where you kind of replace the hash function with a random function for as a thought experiment, and you give everyone access to. She's not looking. You give everyone access to like a box, right? So anyone can consult this box, and if two different people consult the box separately, and they ask the same question, they get the same answer. Otherwise, they'll get independent random answers, right? So that's the functionality of the random oracle. And in practice, what happens? Is there an echo? Or maybe should I turn off my audio?
No.
I heard that. Okay. Pretty sure it's echoing on.
Yeah.
Oh, okay. Oh, there we go. So in implementations, random function is replaced with cryptographic hashing. Just to be a bit philosophical, you do have to be aware of like drawbacks of using the random oracle model. So there's what's called like uninstantiable schemes, meaning that you can prove as some scheme secure in the random oracle model, but there's no way to actually instantiate the random function with the real hash function so that the scheme stays secure. You can see what, for example, I mean, actually the paper that showed this CGH, they wrote, it was like a interesting result, right? And they wrote 3 separate conclusions for the paper, one for each of the authors, to give their take of the results. So here's Shai's take of his result. Oh, sorry. So you can read, if you like philosophy, you can read the text. Okay, but anyway, in this talk, we're going to be okay with random oracle. And I'll talk about some work on removing random oracle at the end. Okay, so now some of you may actually not know what is tightness of a security reduction. Tightness is a quantitative metric of the quality of a reduction. Okay, and its importance in practice was brought to light basically in the 90s by a series of works by Bellare and Dai. And I think at least for work on standard cryptographic primitives like encryption and signatures and now and so forth, now it's pretty widely accepted as important. So let's motivate it via a question. So my question is, suppose we want to use Schnorr signatures over twisted Edwards curves with 128-bit security. How large does the group order need to be?
Usually we set it to be like
256, yeah. Any other comments about that? Okay. So in my experience, it depends who you ask. So practitioners will indeed say that you should set it to 256 bits. But if you ask some theoreticians, they say it's should be set quite a bit higher than that. On the right, Poincheval and Stern, the original proof of Schnorr in the ROM was due to them. Yeah, reminding.
I see. So they say that because we have like cube, like n to the cube.
I'll explain it. Yeah. So So who's right? Hard to say, right? So let's investigate. So how does this discrepancy arise? So the answer is that it's really a consequence of the large gap between the best known upper and lower bounds on the security of Schnorr in the realm. Practitioners ask what the best known attack is, right? And since basically the best known attack on Schnorr is just breaking discrete log in the group, right? So, and that takes order square root p time. So that's how you get, if that's the best attack, to get 128 bits of security, you need 256 bit curve, right?
The big step, giant step.
Yeah, that's one. And there's also like Pollard row and probably some other algorithms. Theoreticians ask a slightly different question. They say, if I'm given an attack on Schnorr signatures, can one construct a discrete log adversary on the underlying group that contradicts our beliefs about its hardness? So like in a 256-bit group, if I have an attack on Schnorr, does that contradict my belief that discrete log is hard on 256-bit curve, right? So, and so let's see what kind of like the theoretician's calculation is here. So here's the theorem that Poincheval and Stern proved, kind of stated in modern language. So I guess probably you're used to reading these theorems, right? So it relates the advantage of two different adversaries, A and B. A is an adversary against the Schnorr, and B is an adversary against discrete log. And the relation is that the advantage of A is upper bounded by QH, so that's the number of queries that the adversary makes to the random oracle, times square root of advantage of B, plus some other term which basically you can ignore. So the important thing is, really it's going to be the square root that kills us, but also the QH is important here. Okay, and so what that means is that, like, you know, if you say, well, look, twisted Edwards curves have k over 2 bits of security when group order is 2 to the k. So if we plug in 2 to the minus k over 2 for advantage of B and say, like, the adversary can make, I guess 2 to the 64 is a good estimate of like the number of hashes the adversary can compute, then we get advantage of A is at most about 2 to the 64 minus k over 4. And we set this equal to 2 to the minus 128, so we get k is equal to 768. So that's how they get 768.
What's this B and this A?
So A is the assumed adversary against Schnorr. So if you have an adversary A against Schnorr, there exists an adversary B against discrete log, such that this relationship between their advantages is true.
Okay.
Okay. So so this square root is like, I guess we don't really cover it in the talk because it's not relevant for our new stuff, but it's due to this fork. So Poincheval and Stern introduced this forking lemma, which was very influential in a lot of subsequent work, and it has this square root term, which really kills the concrete security. Okay.
So it shows that they were wrong.
No.
Like 768 is wrong.
No, it's just another data point. Like, I mean, it depends on what assumption you want, because we show it's the right answer under a slightly stronger assumption than discrete log. So maybe they're not willing to assume that stronger assumption. Yeah, so what we want is to give a tight security proof where the running times of the assumed forger and the constructed DL adversary are the same. That's what we'd like to do. More generally, we can ask, is there tight proofs of security for Schnorr signatures? If so, under what assumption? It's definitely true for some assumption, like if you assume that it's hard to forge Schnorr, then you get a tight proof of security for Schnorr, right? So there is some assumption, but we want to kind of minimize the assumption to the extent possible. Okay, so
anything not known, like static?
Static?
It means it's plain.
All the messages in front.
No, I don't think so. I don't think even there, if you know all the measures, yeah, like selective security, you mean, right? Yeah, I don't think there's any better result for selective. I'm not aware of any result. So let me talk about some prior results that I'm aware of. So here's some papers. So this problem is not new. This problem is has been studied and in a sequence of work. So like the first paper was Poincheval and Stern. They showed in the ROM they showed a non-type reduction as we saw. They assumed DL, right? The interesting work of I guess this is not as well known. Paye and Vineyard. They didn't use the ROM, but they only showed key recovery security. And they used one more discrete-log, which is quite a bit stronger than discrete-log, but at least the reduction is then tight. But more relevant to our work is this Bellare and Dai paper. So they get what's called a semi-tight reduction, meaning they remove the square root term, the square root on the advantage of on the right hand side. So the square root, but not the QH. So that still doesn't give you a very tight reduction. If you work out the parameters you would need in order to support like 128 bits of security, assuming such a reduction, it's still a lot higher than 256 bits. And they introduced a new assumption called multi-base discrete-log, which is kind of similar to one more discrete-log, but different in some ways. And then it's been shown that if you use the AGM, then you get a tight reduction. But like in the context of our work, that's like an overkill, right? We don't want to use, we just want to use the normal ROM. We don't want to, I mean, this should say actually, sorry, I guess I should say like, no, this is all using, yeah, okay, so it doesn't just say. So use the ROM and AGM, both, and you get a tight reduction. And then there is the nice work of Rotem and Segev, which gave some improvement on the exponent, a half, but still not very tight. And they use something called high moment discrete-log. There's a 3 halves or something, or 2/3. I forget what. Yeah, 2/3. Yeah, sorry, I always mix it up. 2/3.
So just trying to understand what type means again. Is it bridging this gap between like 756?
Yeah, so it means that like if you want to know that like in the best case scenario, if you have an attack with some complexity against the scheme, you have the same complexity of the attack against that something. Okay, so my main point from this this slide is that getting even a semi-tight reduction currently requires interactive, non-falsifiable assumptions. What does that mean? I guess probably you know what interactive means. It means like the adversary has some oracle access. And then non-falsifiable means it is not possible to efficiently prove you found an attack. Like, you know, something like discrete-log is falsifiable because if I give you a challenge and you give me the discrete-log back, I can verify that you indeed solved the challenge, right? But there's some assumptions, like for example, one more discrete-log, you have a discrete-log oracle which cannot be efficiently simulated, right? So if you say like, I can break one more discrete-log in your group, I can't even verify that because I can't run your adversary. So basically, such assumptions are not so good because they're hard to, I mean, something like one more discrete-log is not an attractive target for cryptanalysts. And the proofs, I mean, as I said earlier, like the proofs kind of move towards tautologies, right? Because like one more discrete-log is an interactive assumption. So is, you know, the assumption that Schnorr is secure in a random oracle model. So like if you prove something under one more discrete-log, I mean, formally speaking, it's not clear why your result is better than just assuming the scheme is secure in the first place. Cool. Okay. So interestingly, I don't know how many people know about this, but there's a line of work on negative results for this question as well. So this line of work kind of culminated in showing that there's no, like, quote, tight and generic reduction from a representation independent, non-interactive problem to, I think maybe I mixed those. So maybe it should be no reduction from Schnorr signature security to a representation independent, non-interactive problem, right? So if I'm using I haven't told you what representation independent means yet, but if I'm using a representation independent problem and I'm using a generic reduction, then I'm not going to get a tight security proof according to this result. Okay, and I guess maybe generic means that you treat the underlying group like a black box. And RI is more interesting. RI says that basically, if you have a valid, so say I'm working with respect to some group representation, right, for my group, and say I have a solution to the problem, like think of discrete-log, right? I have a g to the x and I have x. If I change the group representation, that g to the x and x is going to stay. I mean, under that transformation, it's going to remain a solution to discrete-log, right? And that general property is called representation independence.
Sorry, I didn't understand that. Can you say that again?
So assumption is called representation independent if solutions are invariant under change of the underlying group representation.
Oh, okay.
So if I change the group representation, like a solution will remain a solution and a non-solution will remain a non-solution. Yeah. So actually that's a good question, but I think the answer is that generic is referring to the reduction, how the reduction treats the group, and representation independent is referring to a property of the underlying assumption. Yeah, but they are quite related. You're right. Okay. So the problem here, I mean, is that you say, so like most of the assumptions we have are if we want to use a non-interactive and falsifiable assumption, most of the assumptions we know are representation independent, like a discrete-log or CDH or DDH or Huber assumption are all representation independent, right? So it's hard to even think of what would a representation dependent assumption look like, right? But apparently we have to use one. So I mean, the general question here is like, is there a representation dependent assumption, which is not, we want non-interactive and falsifiable. So is there such a representation dependent assumption, or you could use a non-generic reduction. In our result, actually, we do both. It gets around the above. So can you give a tight reduction using either a representation dependent assumption that's still like falsifiable and non-interactive, or potentially use a non-generic reduction? Some way we have to get around this result, basically.
Is that what inspired this work?
Mm-hmm. So now it's time for the main event. So here's like our candidate representation dependent problem. So we're going to augment discrete-log with a function. So the assumption will be defined relative to a group and some function on the group. Okay, and the function maps to ZP. Okay, and we say that, so let me go through the game. So on the left is discrete-log, just for the reference. You can see that the initialized procedures are the same. The finalized procedure is different. The finalized on the right-hand side for CDL, the adversary spits out R and Z, and the finalized procedure checks that f of R is not equal to 0, and it checks that G to the Z is equal to R times H to the f of R. So this comes from Schnorr's verification equation, obviously, right? So we say that like, oh yeah, so this is the advantage, and we say that like CDL holds for G and F if it's hard to win this game with any good advantage. Yeah. So this assumption can be, as long as F is efficiently computable, this assumption makes sense for any F. So we want to know, like, for which G and F it's true, right?
What obvious F is discrete log.
Boy, it's not efficient, right? It's not efficient, yeah. F needs to be efficiently computable. It's a bit of a stretch, but R occurs both in the base and the exponent. I guess if you have a better name. Okay. So everyone get the assumption? So you can see why F of R should not be 0. Yeah.
Because otherwise it's trivial to put C as.
Yeah, you just choose. You choose R such that you know the discrete log of it, and then you output that as the C. Okay, so I'd like to point out that CDL is non-interactive. I guess that's obvious. Falsifiable, meaning like given G and F, if someone claims they can solve CDL with respect to this group and its function, I can check that. And then do people see why it's representation dependent? Let's go back to this.
Well, I guess the representation that makes it whether F of R is 0.
So what's the representation independent mean? It means that if I change, so if I have a solution to CDL and I change the group representation, it should remain a solution, right? And I claim that's not the case. And my question is, why?
I mean, is this is very compact.
Mm-hmm. Yeah, exactly. So the reason is because little f is sensitive to the representation of the group, right? If you change the representation of the group, I mean, f of that element may behave unpredictably, right? You don't know what it's going to be, and it may well not be a solution to CDL. So that's how we. I mean, this f is like crucial to getting this representation dependence. Yeah.
I mean, you can literally, I think, change
It's
the group.
just how the group is represented as bit strings.
But you can also just totally change the group, and that's part that would always.
Yeah, I mean I mean all cyclic groups are isomorphic, but
Yeah,
like I'm saying, like if you yeah, it's just like I just mean the encoding of the group elements as bit strings. Yeah.
Essentially, you're redefining the group population. So that now looks as if you.
Yeah, you can think of it as permuting, I guess, as long as it maintains the same group.
Yeah, but
Even if all the groups are isomorphic, though, some isomorphisms are. It also matters what representation.
Yeah, I don't think this is talking about. I don't think of representation dependence in terms of like isomorph. I just think of it as like if you change the bit representation of the group, meaning like what strings represent what group elements, like it should, like a representation independent assumption should, like a solution should map to another solution.
yeah, for example,
The what?
Little endian versus big N.
Yeah, I mean it should, yeah, right? Because think of how like discrete log behaves, right? Like if you have a group element and you have its discrete log, you change the representation of the group, it's still going to be the discrete log of the group element, right? No matter what you change it to.
so as an example, you could change the operator to be permute the elements, perform the operator, now undo the permutation.
Hmm. Okay.
So you back this reduction and reduce this for discrete log in some model.
Yeah.
So what assumption do you need on F for those reductions?
You need like well spreadness. So F actually, yeah, it's a good point. So you can see that like if F has a preimage set that's too large, you can break CDL. There's a generic attack. So if F, like say like, I don't know, 3 or something has like a lot of like way too many preimages, then basically, yeah, I guess I don't remember the details offhand, but you can get like a simple attack against CDL. So it's like in generic models, it's necessary and sufficient to have like a well spread.
the pre-image set is still, say, a negligible portion of the overall space.
As long as there's no pre-image set which is like the chance, I mean, if you pick an element at random,
Right.
it should have a negligible chance of falling in any particular pre-image set.
Makes sense, but it could be the case that, say, you divided the space to X pre-image spaces, and then each pre-image space itself.
Is that possible? I guess so, yeah. I think so, yeah. Yeah. Good question. Okay. So our first main result is that there's a completely tight reduction from. So if you give me this is actually a very interesting thing is like this F occurs only in the proof. So we don't change the Schnorr scheme at all. It's still in the ROM, but F is used in the proof, right? So like if you have a G such that there exists an F such that CDL is hard for G and F, then I can give you a tight reduction from Schnorr security to CDL in the underlying group, right? Yeah, because well, I mean, because if CDL is false, if you have an F for which CDL is false, then the reduction is trivial, right? So if you have a F, yeah, if you don't even have to like, our result just uses F in the group in the proof, so you don't even really have to know what F is. But if it exists, then like like Schnorr does have a tight security reduction. And yeah, I mean, interesting thing is like we have a term proportional to the pre-image size of 0 on the right hand side. So like if there's too many elements that map to 0, I can send you the slides after. Yeah, don't worry. If there's too many elements which map to 0, then that's also a problem for our reduction.
So why is it?
Yeah, because basically you lose in this CDL game if your R maps to 0 under F, right? So if you choose an R and Z such that F of R is equal to 0, and it's kind of like if there's too many pre-images of 0, that has too big of a chance of happening in our reduction.
So adversary will give you a lot of.
I think it's like because you kind of get, well, I guess we'll see where it comes up in the, yeah. Okay, so let me just, I'm just gonna give you like some vague intuition. So we want to know like how to reduce Schnorr to CDL. So CDL for a CDL adversary, we get an instance H, which is just a discrete log instance, right? And we run the forger with the public key H. And the signing queries that the procedure for the signing queries is not different than any other. I think all of the proofs for Schnorr I'm aware of do the same thing when they handle signing queries. So you just basically program the hash. You choose R in like a way such that like if you program the hash function at M and R, then you can create a signature.
Wouldn't that create this like Q to QH loss, factor loss?
No, I mean, because you choose R freely every time a signature query is made. So you can just choose a convenient R. I mean, you can choose R that like, I mean, basically what you do is, let's see if I remember, you choose R is equal to,
I
some
see.
ratio.
I think the QH is maybe like you guess the random oracle query.
Yeah, QH is guessing the random oracle query. That you don't have to guess it when you sign. It's like you guess it for the forgery, I think, maybe. Yeah, so I don't remember the details. So, but like, okay, so perhaps, so the more interesting thing is like what we do to handle hash. Everyone's good with this? So what we do to handle hash queries, we want to basically embed outputs of F in the responses such that, for one, the forger cannot detect these embeddings. And the forgery can be used to extract a CDL solution, right? That's basically the strategy. So it's actually pretty simple. So what we do is on the ith hash query, we choose, so say the ith hash query is R and M, right? So we choose R prime to be R times G to the AI times H to the BI, where AI and BI are random in ZP. And we set the hash value, we program the hash value, right? Because we're in the random oracle model, so we can program. We program the hash value to f of R prime plus AI mod P. And AI and BI kind of ensure independence between R prime and f of R prime. I mean, sorry, R prime and the hash value that gets returned. Okay, so now suppose the adversary's forgery is M, R, and S, and so we have this maybe corresponds to the J hash query, right? So then we have this equation here, G to the S is equal to R times H to F of this thing. I mean, this is just plugging in the definition of what we had, right? And then, and you multiply both sides by G to the BJ, we have this equation, right? And then you can see that it's simply, if you set Z hat and R hat to this, then it's a solution to the C. So it's, I mean, this proof is not, I think the hard part was coming up with the assumption, not so much coming up with the proof. Okay, so now, so we have a little bit of time, so I want to talk about, yeah. Yeah, that's a good way of thinking about it. I mean, well, oh, you're asking if CDL is random self-reducible.
I mean, so like a random. You can solve a random thing. Yes. Yeah.
I think it probably is.
Probably depends on that.
It depends on. Yeah, maybe we should talk about it. I'll have to think about it. I think we considered that at some point, but I don't remember what the answer was. Yeah, so now I want to talk about extension to threshold signatures.
Before that, just a quick question about the previous slide. So why is this new R hat satisfy f of R hat is not 0?
Oh, so AJ and BJ are random, right? So it's, yeah. So that's where the preimage, see, that's where the preimage size of 0 comes in the proof. No, it's like very elementary. It's just like a random element. If we use the fact that if you compute f of R for random R, it's unlikely to be 0, and that's because we have that term in the bound. Okay, so let me talk about like another timely topic, which is threshold Schnorr signatures. So as I mentioned, Schnorr signatures are used for a lot of types of advanced signature schemes, right? And we'd like to basically, I mean, a broad research goal is kind of extending the reach of CDL to these various advanced types of signature schemes, right? And so in this work, so far we consider a threshold Schnorr signature. And in a threshold Schnorr signature, T out of N threshold Schnorr signature, the secret key X is secret shared among N parties via T out of N Shamir secret share, right? So, and then any subset of at least T signers can produce a Schnorr signature under the corresponding verification key G to the X. Sense? Yeah, so TSS is really popular now. There's a lot of work coming out on it, and because, well, at least in part because of its application to cryptocurrency. So there's like actually in preparing for the talk, I asked ChatGPT like what are the applications of threshold Schnorr signature scheme, and it gave me like a ton So in like even in just blockchain and cryptocurrency alone, there's like 10 different applications. Okay. So you can think of either when a threshold signature is created, you could either think of a leader being external to the parties that are signing, or the leader being one of the parties themselves. So here, just because it's easier to draw, I'll consider an external leader. So this leader wants to kind of like conduct a protocol with the parties where like, so here I think we consider like, and in this example, I'll give you, we consider like 2 out of 6 secret sharing, right? So the leader should talk to like 2 of the, if the leader talks to 2 of the signers, he should be able to coordinate like the construction of a Schnorr signature under G that verifies with respect to G of the X. And the XIs are all the secret shares of X. And the other thing is that like in practice, I guess you probably don't want to have a trusted party do the initial secret sharing. You would use like a distributed key generation protocol, but I'm not showing that because it's a little complicated. You'd also, in that case, you would publish the G to the XIs as well, because that would be like verifiable secret sharing, right? But we don't do that here for simplicity. Just assume that everything is pre-shared. Okay, so the first thing the leader does in this example is send like so the leader is going to sign with going to get 1 and 6 to sign. So she tells them, okay, 1 and 6 you're signing. They're going to compute some R1 and R6, which R1 little R1 and little R6 are random, and send back R1 and R6. Okay, the leader computes R as the product of R1 and R6. And sorry, I think I had it. It's supposed to be M and R. Yeah, sorry, I just made these slides. So it's supposed to be M and R. Here, I'll show you. So this, after this R is created, it's supposed to be M and R are then sent to 1 and 6, player 1 and player 6. Then player 1 and player 6 do this local computation where they hash M and R. Okay, and they compute like a share of the Schnorr signature using the Lagrange coefficient corresponding to their position, right? And then these are sent back, Z1 and Z6, the shares are sent back, and now R and Z are, now the leader is in possession of a Schnorr signature once they add Z1 and Z6. So R and Z is a Schnorr signature with respect to G to the X, and that's what you want. Make sense? Yeah. You can assume that so let's assume that they see it. I mean, in general, like there could be different setup assumptions. Yeah, I'm brushing a lot of things on it because you also have like synchronicity assumptions and stuff like that swept under the rug. So yeah, I'm just trying to convey like the high level, I guess. But those are definitely issues you have to think about if you're going to actually use it. So one thing I want to make clear is that in proof of security for Schnorr signatures, to answer a signing query M, the reduction picks, so this is what we were talking about earlier with the signing queries, right? So the reduction picks R depending on M, and then programs the hash value of R and M. That's like, in all of the proofs for Schnorr that I'm aware of, that's what you use to answer signing queries. And what the problem is that in the threshold setting, you kind of can't pick R dependent on M because M is picked first, right? So basically, so like if you think of picking, imagine you have like a, let me go back to this slide.
Yeah, maybe try and wrap up in 5 minutes.
Okay, yeah. I'm forgetting what I was supposed to say. So you basically don't have this luxury in the threshold signature scheme of picking basically the parties contribute their R values before seeing M. So there's like the I signer contributes RI before seeing M. So you can't do this proof. And indeed, like there are attacks. And so in the naive signature scheme I mentioned, there's actually like a polynomial time attack, right? So you can't do that. And another concern is rushing, where corrupt signers RI depends on your RJ, right? So you can like influence what's the final value of R in the signature. So the question is, how can we modify this? This is like the very naive scheme that if you just sat down for 5 minutes and thought about how would I design a threshold Schnorr signature scheme, that's what you would design. But then there's these attacks. So the question becomes, how can you augment the scheme to prevent these attacks? And two popular solutions that are in the literature, one is called Frost, or Frost 1 and Frost 2, right? So this is kind of a scheme which popularized this topic of threshold Schnorr signatures. So the idea is that the leader, I guess in this case, would shift R via like multiplying by S to the delta, where the signers, in addition to the R's, they also choose S's. So like in addition to sending the G to the RI, also send a G to the SI. And the final R, which is used to sign, is the old R times S to the delta, where delta is like a hash of all the RI and SI. And it basically kills the attacks.
The reason is that you get to pick the hash output after or something.
The reason why this works, or because like if you basically change the RI, I think the hash value, the delta changes. So there's some like circular dependency on like the attack would not work if when you change R, like when you change RI, the R changes in like an unpredictable way, I think. And then the other scheme which is quite popular is Sparkle Plus. So there's more schemes. I mean, there's a rich literature on this, but I'm just focusing on like a couple schemes that are kind of actually like NIST has some. I don't know if they have a call for standardization, but they have some documentation on threshold signature schemes, and I think Frost and Sparkle Plus are the two main schemes they're considering. So Sparkle Plus does something else. They add an extra round at the beginning where the signers send commitments to their RIs and then basically open the commitments after they verify all the other commitments, and they send signatures on their views. And finally, signers verify consistency of the views and send their shares of the final Schnorr signature. So basically, they get around of this. They say that like you first have to commit to your RI before you, and then like everyone commits to the RI, and then only then you reveal. So it can't depend on, like my RI can't depend on yours because everyone already committed. So type reductions. Oh yeah, I'll wrap up in like 3 minutes or something.
Yeah.
Okay. So let me just end with the Sparkle Plus result, and then that's fine. So the type reductions are kind of novel in the context of Schnorr threshold signatures. Most works don't consider them. And we focus, in this work, we focus on tightness of Sparkle Plus under static corruptions, meaning that the players that the adversary corrupts is declared at the beginning of the game. Adaptive corruptions are much harder to handle. The reason is because Sparkle Plus under adaptive corruptions and even Frost under static corruptions requires like very strong, it's not like AGM or one more discrete log type assumptions. So those are not really friendly with CDL. So if we want to use CDL, we like to consider Sparkle Plus under static corruptions because the existing proof for Sparkle Plus under static corruptions only uses DL. So it's plausible that you could tighten it using CDL. Right. So yeah, so all of these reductions for all of these schemes are quite loose with the bounds analogous to what you have for classic Schnorr signatures. And there's not been like for Schnorr, at least we have attempts to improve the tightness, right? We have like the Bellare and Dai result and so forth. There's nothing like analogous like that for thresholds. Yeah, so I have here the other main result, which is basically proof that CDL, that Sparkle Plus is tightly secure under static corruptions, assuming CDL. And this is like, I remember I said that the Sparkle Plus uses a separate signature scheme to sign the views of the signers, of the players, and we need multi-user security for that signature scheme. The nice thing is that if you use Schnorr as that signature scheme, also use Schnorr as that signature scheme, Schnorr is tightly multi-user secure under CDL, so the whole thing is tightly secure under CDL. No, it's because of like re-randomization property. Oh, sorry, what were you gonna...
What's multi-users?
Oh, like where the adversary can request to see signatures under different secret keys for different users.
Oh, and needs the fortune.
So skip this. So let me just go to the, I'll go to the open problems because I think that's probably what most people are interested in. So here's some juicy open problems. So one problem I'm interested in is like, suppose I give you a group like elliptic curve group, right? Like, can you tell me a function for which a CDL with respect to that group and that function reduces to some standard assumption in that group, maybe even discrete-log? Interesting point is that a tight reduction to discrete-log would not contradict the impossibilities because our reduction is not generic, like it computes f, which is a non-generic function. So it wouldn't, so you could potentially have a tight reduction from, so it might, I mean, CDL may potentially introduce a new path to proving tight security of Schnorr under DL itself. And another question, like, is CDL applicable to additional Schnorr threshold Schnorr signature schemes or the other kind of advanced signature schemes, like I mentioned? And then one thing I want to say in closing is I think a really important problem is instantiating Schnorr. So I'm not aware of any significant positive or negative results about replacing the random oracle in Schnorr with any concrete hash function. And I think that would be a really nice and timely result since it's being used all over the place. And I think potentially CDL could be useful. I mean, here's one question, right? So if I have a function that satisfies CDL with respect to some group, can I then build a function which can instantiate Schnorr in the group? I mean, that's a natural question, right? And in fact, CDL, you can think of it as saying that you can instantiate Schnorr with the empty message and no signing queries. That's exactly what CDL is. So basically, I'm asking, can you like bootstrap that to full unforgeability? Yeah, cool. That's sorry. That's hope I didn't go over this.
That's fine. We started late too.
Yeah, yes.
Cool.
Thank you.